You did. I don't think so. All right, so there's the square root. Okay, then we're going to copy. Okay, you got to make sure everybody can do this process. And then we're going to do what? We're going to graph the absolute value. You can type ABS, or you can just do this. And we're going to paste that in there. And we're going to graph it, and then what? We're going to do a zoom fit from 1 to 4. Now, another thing you want to be prepared to answer here is, well, not necessarily on this one, but understand, okay, so let's talk about these error formulas. So what these formulas do is give us what? What is that number that gives us? Max error. That's what we want to understand, right? It gives us the most that approximation is off. So we're doing this for an L3 or an R3 right now. So it should tell us the most it should be off. Okay, now that's based on what, though? What's that based on? Well, no, yeah, but what's the key component of this? What's the key component of this formula? The K1 and the K2 value. Because what do those represent? The most slope or the most curviness, right? The worst case scenario, right? The thing that's causing the error, the thing that's causing the approximation to be off is the steepness or the curviness, okay? And so the K1 value, that number in the box, is assuming that it's going to have that amount of steepness the whole time when clearly it's probably not. So what number are we going to use here? Where's our K1 going to be? Right there. Now, if this graph comes down like this and then levels off like this, how does that compare to if this graph started up here and then kind of went like this? How would that matter? If this graph was here and went down like it does, or if it was up here and just kind of was pretty flat. Your approximation error, when you talk about the max error number you get,
it's going to be the same.
Well, the calculation's going to be the same.
Yeah, but the number's going to be smaller.
What number?
Like how much you're going to be off by.
No, it's not. It's going to be used 0.51 either way, no matter what the rest of the graph is.
Well, I think you're both right. I think you're saying two different things. The formula number that we calculate, that max error number, is going to be the same, right, is what you're saying. Because you're going to use this number either way, right? So you're going to get this number that's like, let's say it's 0.5. So that's saying the most you can be off is 0.5. But now what are you saying?
Saying that since it's like that max slope, won't it be like less, it'll be closer, the approximation will be closer to the actual value.
Are you saying because...
No, because this isn't the F graph. This is F prime.
Won't it still be closer though?
What do you mean?
Just because all the slopes are more consistent, it's going to be flatter.
Well, it doesn't mean the graph's going to be flatter.
No, but since all the slopes are similar.
Okay, right. I think you're onto it. So in other words, if we get a max error of 0.5, does that tell us that that is the amount of error? The amount of error might be a lot less than that, right? Our approximation might be pretty close to the actual area, right? Or it could be way off, right? In this case, I would say it's going to be more way off, right? Because our formula is assuming that the slope's going to stay up here, and it doesn't, right? It gets way less. If the slope gets way less, that means it's flatter. F is flatter, right? Which means your left and right rectangles are going to fit better. So you're going to have less error in this situation. Less error, but your formula number is going to be off more. Does that make sense? I mean, because our max error, so it's not going to be as good of an error bound in this one, right? It's not going to be as good of an error bound. It's going to say we're off by, say, 0.5, but we might really only be off by about 0.1 or 0.2. Because, right, does that make sense? So it's kind of, so I think you guys were both saying the same thing, but you were just getting at a little different, right? So the more consistent the F prime graph is, then the better error bound we'll have, right? Well, that's kind of what number 27 gets into, which I want to start a little bit, but I don't want to do it. Well, we'll do a little bit of it, so you guys can have a chance to do it too. Okay, so anyway, back to this. So what number, what was that number, Matt, Will, did you have it?
The max was 0.5.
Oh, it is 0.5?
Yeah.
Oh, well, I'm just guessing. I didn't know that. So if, you mean if we just trace right at 1, so it's exactly that?
Yeah.
Which I guess makes sense, could be, yeah. Now, if you get a case like that, where it's exactly 0.5, you could use 0.5. You wouldn't have to round it up to 0.6. Remember, you want to pick a number that the slope will never be more than. Well, if it's exactly 0.5, it's not going to be more than 0.5. Where we want to round up is if we got that decimal that keeps going and going and going. Then our last number we want to round up. Okay, so here we can use 0.5. All right. So what does this work out to? How much? 0.75. So is that consistent with what we found here and here? It is. Because what does this represent? This is the most we could be off. And this is how much we were actually off. Right? So that's consistent, right? So and remember, we said our error bound wasn't going to be as good because it came down, and so we assumed it was 0.5. We assumed that F prime value was going to stay 0.5 the whole time with using this formula. It clearly doesn't. It was that at the beginning, but it went down. So our max error is going to be a ways off of our actual error, right? Our actual error resistance. That's okay. What we want, remember what we want is we want a guarantee. And so when we do the thing that says how many rectangles does it take to guarantee 3-digit accuracy, we don't care if we have to do some extra. We just want to make sure we are guaranteed 3-digit accuracy, right? And so we would use this 0.75, we would use that number, and we'd say, okay, we need this many rectangles that guarantee a certain amount of accuracy. So we're not expecting this error-bound formula to give us the amount of error. We're wanting it to tell us the most error that there is, okay? So it's important to understand that. All right, then you had to repeat the same thing with midpoints and trapezoids and use those formulas in K2 and all that, okay? All right, let's take a look at number 27. I want to talk about that one a little bit. And that gets to this same idea. So if we take this function here, okay, if we take cosine of 1 over x, and if we go back here and we do the derivative of that, okay, and so cosine and we're talking about lefts in this one, okay? And then we want to, what's our interval 1 to 11? Oh, I didn't zoom through. So what do you notice here? 1's the max, but based on the discussion we just had.
max error is gonna be way far off.
Our max error is gonna be way off, right, of what the actual error is, because we're gonna assume whatever this number is here back at 1, 0.84 what?
So I had my error was 0.841. I just K1 is 0.84.
841?
Yeah.
I think we're gonna round that up,
So
because it's not exact.
Is your-
Pretty, why is mine not floating 3? I thought I fixed this yesterday. Yeah. It goes back all the time to that. Okay, so I think, see, so that's gotta be 842. If you see 841, that's not if I see 0.5 or I see 0.75, then I know that's exact probably, right? But I'd make sure and go to your settings when you're in here and make sure, yeah. So you wanna use 842. Okay, we gotta round that up. We gotta round that number up, because again, we're trying to get a number. Now, this one's gonna be so much more, right? I mean, would you still have really a guarantee? For sure you would. But again, that's the principle of the thing here. So I want the number. I want 842. Okay. Now, clearly, most of the time, this slope, so that's saying we're going to assume the whole time this slope has a graph of almost 1, right? Which is going to make those rectangles off. But most of the time, the slope is almost 0, right? Which means the rectangles, for most of the time here, the rectangles aren't going to be very far off at all. Because this graph, these values are down around 0, which means if we were going to graph the F graph, it would be pretty flat. Okay? So, anyway, so here's the actual answer here. On 27, I just did that. It said, what's the smallest n that guarantees you're within 0.005? Okay, so we need a K1. We're going to have 11 minus 1 squared over 2 times 10. 2 times n. We don't have, yeah, oh yeah, we don't know n. Yeah, 2n. 2n. And we want that to be less than or equal to 0.005. Okay, so and what did you say we had? 842? Okay, so let's solve that. What do we get? 8,420. Okay. Now, I don't know if you looked at the back of the book. Bodie came in this morning. We were talking about. He looked at the back of the book, and it was weird. Now, I think that number was okay, but then in B and C, it had some weird numbers in it. And they're better. The numbers are better in here. Now, they use 0.85, I think. I think they use 0.85 as in the back of the book here, in the back of this answer book. They used 0.8415. I'm sorry, they went one more decimal place. They went 8415. So they had 8,415. So that means we would need 8,420 rectangles, okay, to be accurate. But probably we need way less than that, right? I mean, probably we need way less than that to get 2-digit accuracy. Okay, so now, but here's the part then what we could do. So then in part B and C, they do this. They say, let's split it up from 1 to 6. And we said we want the error to be less than 0.005, right? Well, most of the error is going to be in the beginning part of that graph, right, where it's steeper. So let's split up that error, that 0.005, and let's do 0.004 of that error in this interval and 0.01 here, right? And let's see how many rectangles we need if we split it into 2. Okay, now it might be better to split it into even smaller increments, but they just split it in half, right? 1 to 6. Okay, so now what would your K1 value be from 1 to 6? Still be 0.842, right? Because it's still at 1, right? And then you would have 6 minus 1 squared over 2n less than or equal to 0.004. Okay, solve that. What do we get? Did you do that, Jesse, already? 2,600. Do you use 842? Okay, and the answer book here, using their number they used, said 2,630. Okay, so roughly, right? So we needed 8,000 to guarantee the whole, over the whole interval. But we really only need 2,600 in that first half if we just split it up into there. And then what about this half? Now, what would we use for our K1 value here? We would have to go back and find it. Right? So we're going to have to go back in here and trace at what? Chances are it'd be at 6. So what? 0.00. Yeah, I'm not sure I'd go 5. I think 4.7 or 4.61 even. Because once you get past those zeros, I'd rather go past those zeros and then think about 3 decimal places there. So 00, let's go 0047. Okay? It's not a guarantee. I don't want you to just think 3 decimal places. It's not always 3 decimal places. If you've got some zeros there, I think you probably better go a few more past those zeros. And if you've got a bigger number like 28 something, 28 point something, you may not need to go 3 decimal places. Okay? What does that come out to be? Using that number? Okay? Isn't that interesting? I mean, so then add those together, right? So really, if we split it in 2, we could do it with a lot less rectangles and have the same amount of guaranteed max error of 0.05. So they split up the error, they split up the interval, and again, we could probably go from, to be honest, we could even reduce that number more if we went, because this drops off so drastically. This is taking forever. Just go 2, there's 2 out. Right? We could probably split it from 0 to 2, right? Because it went from a slope of 0.8 already down to 0.1 right there. So we could probably just go 0 to 2 and then go from 2 to 11 or for sure 3. We could go 3, 0 to 3, and then went 3 to 11. We could have split it up that way and probably drastically reduced the number again. But the idea is, it's not so much about application. Probably with the speed of calculator, speed of computers, you could take that whole interval. You could say, okay, it's going to take 8,000 rectangles. Let's just do 8,000 rectangles, and boom, boom, boom. The computer can do it very fast. Okay. If you were having to do it by hand, then it would make a big difference. And cutting it down from 8,000 to 2,000 would make a big difference. And then, of course, if you're doing a Simpsons rule or something like that, we could do it with much less error anyway, much fewer subdivisions anyway. But it's more about the idea and the concept of what's going on. That's important. Okay? All right. So today, rest of the time is, basically we want to sample 3. I think we want to try to have that done by next week for the most part, to where you've worked on those and can ask questions about them come Tuesday. Free response, the whole thing. Okay, that's one. The Niobrara project thing. Now, again, this is the only example I had. A lot of the students that turned in for bonus points were on a bigger poster board, and you notice the way they wrote it out. This is what I'd want to see. They just kind of wrote it out, ... If they were doing lefts or midpoints, rights, whatever you're doing. Then the stream. Now you had 3 pieces of graph paper, so you're going to need 2 pieces across just to fit your river, and then the 3rd piece of graph paper is for your stream. Okay.
Give us bonus points if you write on all 72.
No, probably not. No. And some color. It didn't use any color on his graphic. That'd been nicer. But, he did a little bit here. Wasn't bad. So, what's that?
We just do every other one?
You plot all the points, but the rectangles are too wide. And so when you each of these blue lines would be 2. So you label 0, 2, 4, 6, 8. So your odd ones you would plot in between. So you plot them all, but then your rectangles are too wide. Yes. So I can't, I think
I just was reporting that.
yeah. So, yeah, if this was your graph paper, so if you were, you know, if your lines or your grid was gonna be like, so I don't know, you have to count up and down and see how many will take, what did we say the biggest number was, 75? So I don't know how many numbers you have up and down here. 1, 2, 3, 4,
It's like,
Probably go back.
you go by threes, it's more than 24s.
yeah, you go by threes for sure, probably.
How many is there?
Was that at
I-
least 25?
Yeah, at least 25. I got the 30. I think. Depends how far down here you want to start. So I think you could probably go by threes, fours for sure. You don't go, if you go more than that, then your graph's going to be compressed. So you probably don't want it. But then down here, anyway, so what I was saying, yeah, you go 2, 4, 6, 8, 10. But we do graph every single point. So you want to graph one there, and then maybe one between. It's probably a good idea to connect them as you go. I don't know. Maybe not. Maybe not. And don't just draw lines in between them. Make it kind of a smooth curve. As smooth as you can, anyway. And that's not going to be due till next Thursday. But if you get it done, if you have it done over the weekend and you want to hand it in and get it, you know, out of your hair or whatever, you can bring it in. That's fine. I just probably won't grade them till over spring break.